Good evening, everyone, and welcome to Fiveable's stream tonight on related rates. My name is Jamil Siddiqui, and I will be helping you out with some of these problems this evening. But we're going to be looking at the topic of related rates this evening and how to approach them and how to deal with these complicated and word questions. So, without further ado, let's get started. I'd like to remind everyone that you can follow Fiveable along on all of your favorite social media. We update each day about what posts we're going to be doing, what streams and what topics, and all the different AP subjects, not just calculus, but all the AP subjects you can imagine. So follow us along, and you'll know where we're going. This evening in this stream, what we're going to be doing is looking at related rates, and the first thing we're going to talk about is differentiating with respect to different variables. So we're going to just start off with some easy derivative problems, just making sure that everyone can actually do the computations that are necessary. Then the next thing we'll be looking at is translating these word problems. One of the big things with the related rates is there's just a lot of reading going on. And a lot of times, if we can just translate that into our mathematical symbols, that makes all the difference in the world. And then the last thing we'll talk about is the role units play in related rates and how we have to be aware of the units. So what I'd like to do is just get right into it and start looking at some problems. So we're going to start by just looking at some derivative problems and just computing some derivatives to make sure we can do the skills that are necessary to attack these related rate problems. So in this first example, pretty straightforward. Y equals x cubed plus sine x. Go ahead and take the derivative. Do it along with me. If we're doing the derivative of this one, what we get is the derivative of x cubed comes first. And again, nothing too complicated here. We're just going to go term by term. And the derivative of x cubed is 3x squared. And then we go take the derivative of sine. Again, another straightforward function derivative. The derivative of sine is going to be cosine. Now, the important thing to understand is what happens on the other side of the equation, because what a lot of people don't realize is that when you take derivatives, you're actually taking the derivative of both sides. So over on the right-hand side, I think everybody's pretty comfortable. The derivative of x cubed is 3x squared. The derivative of sine x is cosine x. But it's over on this side that most people just take it for granted. When you take the derivative of y, you write down the notational answer for that. And the derivative of y can be written as dy over dx. Now, when I first learned calculus, I didn't realize I was taking the derivative of both sides. I just wrote dy over dx because I thought I was supposed to. It was only after I started tutoring and teaching calculus that I realized the consistency in math here says that we've got an equation. So the idea is we've got to do the same thing to both sides. So again, this one works out pretty nicely. And I just want to remind you guys of the variables in this problem. We've got x as the independent variable. And when you look over here, all you do is see x's. Everything matches. This is going to work out very, very nicely. So let's just look at another really quick example to get our derivatives up to par. It's going to look very similar. Same exact equation, y equals x cubed plus sine x. But this time, the directions are to find dy over dr. So my question for you guys, and if you could answer in the chat, I'd appreciate it, is what role does r play in this problem? If you look at the equation, you don't see an r, but yeah, I'm asking you to take the derivative with respect to r. So what role does r play? And this is kind of an important thing because this is going to tell you who your variables are. So I see Cole over there giving me an answer, and he's on the right path. And now I got a bunch of people coming in. The role of x, independent variable, all good answers. What I like to do is I like to say the bottom variable there is the independent variable. It's what we're taking the derivative with respect to. Now, that gets a little confusing in this problem at first for people because we don't see an r anywhere in the problem. So what you've got to understand is r is changing, and in turn, since r changes, it makes x change. Okay? So x is changing because r is changing inside of it. So that gives us this idea of a chain rule. So when we go to take this derivative, we're going to approach it the same way. Just remember, the notation for taking the derivative of this problem is d over dr, which that's the big difference between this problem and the last problem. In the last problem, it was d over dx, and we saw x's everywhere, so it was very consistent. In this problem, r is actually playing the role of that independent variable. So if I go to take the derivative of both sides, when I take the derivative of y in this case, I'm going to actually end up with dy over dr because r is our independent variable. Now, as we look on the other side, where we took the derivative of x cubed in the first example, it was very straightforward. It was a one-step. X was the independent variable. Now, X is not the independent variable. R is the independent variable. So this actually turns into a chain rule, like several of you mentioned over in the chat. So when we go to take the derivative of x cubed using the chain rule, we got to take the derivative of the outside first. The outside in this function is something cubed. So the derivative will be 3 something squared. That's the derivative of the outside. We're going to copy the inside, which x is the inside of this problem. And now this is the key. We're going to take the derivative of the inside, and that becomes a notational derivative, because take the derivative of is d over dr, but we're taking the derivative of x. So we simply write dx over dr for the derivative of x in this problem with respect to r. As we continue and we take the derivative of sine this time, again, another chain rule. The derivative of the outside is the derivative of sine of something. That's going to be cosine of something. We're now going to copy that inside, which is x. And now we've got to take the derivative of that x with respect to r. So that's going to be dx over dr. So the idea here is to pay attention to who the independent variable is so that you can know exactly how to write these derivatives. Okay? So any questions so far? If there are, please go over in the chat and we'll go from there. What I'd like to do now is just go and find out how this gets played out in these word problems. So what we're going to do is we're going to take a look at this one, and I'm just going to give you a couple of seconds to read it. A big part of the related rate problem is trying to make sure that you can translate the words into mathematics. Okay, once we can get the math symbols in, once we can figure out these math symbols, the problem becomes a lot easier. So we're going to talk a lot about just translating the English here into some mathematical terms so we can get a handle on what this problem is all about. So as we read this, one of the most important words you're going to see, and actually let me just throw that out to you guys. If you had to pick one word in this question as the single most important word in terms of calculus, which word would you choose? And Karen, thank you very much. You're right on it. Rate, exactly. Yeah, all of you guys are all right. The word is rate, because rate means slope, and slope is derivative. And when you're talking about calculus, there's no more powerful tool than the derivative that we can have. So as we're looking at this problem, what I'm going to do is I'm going to focus on the word rate every time I see it. Okay, so the first time I see rate, right there. So now the question becomes, rate means slope, slope means derivative. What are we taking the derivative of? Okay, so when you see rate, you're thinking derivative. The question you should have is, what are we taking the derivative of? So in my classes, what I do is I make my students circle the word rate and then point to what it's referring to. In this case, if you look at the sentence, we're saying if the radius of the first circle is expanding at a rate of 5 inches per second. So what's going on here? That's going to the word radius. Okay, so that rate is referring to the radius. And what we have to understand about this problem is there's more than one rate. So the first one belongs to the radius. So let me just back up a step and kind of just go over the problem and get a sense for what's happening. We've all taken a stone probably and thrown it into a pool of water or a lake or something like that, and you see the ripples extend. In this problem, if we draw a picture of this and think about it, the stone hits the water and we get the first ripple, and then the ripples start to extend outward. So what we start to do is we start to get a bunch of concentric circles. So what we're being told about this problem is the radius is increasing as it moves outward. And every time the radius increases, we get a new circle, and that new circle has a greater area. So the idea is to find out how these rates are related to each other, hence the name related rate. So again, the key word here, rate, refers to radius. So every time you guys see rate, what I'd like you to do is think about how would you write that using some calculus notation. So rate is derivative. Derivative is usually written dy over dx, but you've got to make it fit the problem. And in this question, y's and x's are not immediately apparent to us. So what I'm encouraging you to do is make the variables fit the problem. So the dependent variable in this case is the radius. The radius is what's changing. And now what's the independent variable? The independent variable is going to be the thing that's changing to make the radius change. And you're going to get a clue on this if you look at your units. Okay, the units are always going to be a really big clue to help you figure out the variables. So when you look at the units on this, what we've got is 5 inches per second. 5 inches per second takes us, and that gives us the clue of what the variable is. The inches measure the radius, and the seconds measure the time. So the way I would write the derivative in this problem is I would write dr over dt, where r stands for the radius and t stands for the time. So the first rate gets translated very quickly to that dr over dt. So now we're going to keep looking, and we're going to find the next keyword in this problem. And that next keyword is going to be the word rate again. So this time when we ask what's changing, well, this time this word rate is referring to the change of the area. So when we go to write this as a derivative, what would be the appropriate notation? We use dr over dt for when the radius was changing. Now we've got an area changing, so the appropriate notation is going to be dA over dt. Okay, so the idea again is, can we take the English words and translate it to math so we can start writing some equations to get this done? So far, I hope everyone's okay in understanding how we're just translating the word rate into the derivative notation. The next thing we're going to do is we're going to go back and we're going to read again, and we're going to try to get all the other information that's in this problem. So dr over dt, we're told something about dr over dt in this problem, and dr over dt ends up being 5 inches per second. So that's what we've got. The next thing we're looking for is we're reading the rest of the problem, and we're going to see if there's anything else that we've missed. As you read it, stone tossed into a pond causes ripples to expand like concentric circles. Not really a lot I can change there mathematically. If the radius of the first circle is expanding at a rate of 5 inches per second, that's our dr over dt equals 5 inches per second. So we're all set there. And then what is the rate of change of the area of the first circle? Here is kind of the important piece of the puzzle. dA over dt here is what we are looking for. Okay, so that's the question mark that we have. That is what this problem is all about. So now if you just kind of think about this as a regular math problem, usually we need an equation and we're trying to solve for something. So in this problem, the question is, what are we trying to solve for? And that's where this question mark comes into play. We now need to get an equation with dA over dt in it. So the idea here is, how do we go and find that equation? Because I don't know about you guys, but in my world, most of the equations I've learned before calculus don't have a whole lot of derivative notation in them. Matter of fact, we have a lot of geometry problems, geometry equations, and you're going to see us using these geometry equations all throughout this session, because related rates is actually very much dependent on previous formulas that you've learned from other places. So in this case, I need a dA over dt. The only way I know to get a dA over dt is to find an equation that has an a in it. Because if I have an equation that has an a in it, we have the power of taking the derivative, and once we take that derivative, that will create a dA over dt. So what we need to do here is start with the equation a, which is area, and since we're talking about circles, the area of a circle equation is going to be a equals pi r squared. Now this equation is our starting point, okay? If I look at my related rates problem, I see dr over dt and dA over dt. What I really need to think about is, how am I going to get an equation that I'm comfortable with from this problem? So what I encourage my students to do is kind of organize their work like this. I say, let's think about organizing our work, and then up in this top right-hand corner, focus on who your variables are. And the variables that we're going to concentrate on are going to be our dependent variables. And in this case, that is r, and that's a. And the only way you get in this box up here is if you have a rate associated with it. So because I have an r in that spot, because I have an a in that spot, I know I want to use these two variables. These two variables are going to be useful as I go through the related rates problem. So the idea is, come up with an equation with the variables in this box right here. So that leads me to area equals pi r squared. We're not going to finish this question until we're able to isolate a dA over dt. So the idea is to take this equation that we've got, a equals pi r squared, and now what we want to do is just differentiate it. Because by differentiating it, we're going to end up getting exactly what we need. So we go and we do the derivative of a equals pi r squared, but again, it's all about doing it with respect to the independent variable. And in this case, that independent variable is time. So as we go through this and take the derivative A, the derivative A is going to be dA over dt. And now on the other side, we're going to take the derivative pi r squared. And I can see some of you guys are doing this over in the chat. That's great. Pi is going to get a free ride. And now because r is a dependent variable and t is the independent variable, this is going to become a chain rule. So we've got to take the derivative r squared as a chain rule. So the outside function here is something squared. So the derivative of that is going to be 2 something to the first. We're going to copy the r, and then we're going to take the derivative of that r. And because r is dependent, the derivative of r is going to be dr over dt. This, to me, is the key to the related rate problem, okay? Trying to find out how to go from an equation that has your dependent variable in it to an equation that has your derivative you want in it. So going back to that page, all we need to do now is just use the information and plug in. So we're told that dr over dt is 5 inches per second. So if we're finding dA over dt in this problem, we now know that 2 pi, I'm still going to have an r in here, but I know dr over dt is given by 5, so I can plug 5 in for that. And what this is going to tell me is that the area is changing, and the way it's changing is whatever the radius is, the area is changing at 10 pi times more than that. So usually in a problem like this, what would happen is they would say, what is the rate of change of the area of the first circle? And usually what they would do is say when the radius is equal to, and they would say something like 10 inches or something like that. Once you know that, you can finish this problem completely, and you would find out that dA over dt is equal to 10 pi times 10, which would give us 100 pi, okay? So now we know the rate of change in the area. The last thing I want to say about this one before we move on to the next example is, where do units come into play on this? So the radius is measured in inches, t is measured in time. Knowing that gives us the clues we need to figure out dA over dt, because if radius is being measured in inches, then area is going to be measured in inches squared, and time is going to keep that same unit of seconds. So when we get this final answer, we're just going to put our units of inches squared over seconds on it. I do want to remind you the consistency that we're going to see is A here, inches squared here. Areas on the top, the units on the top reflect area. Then when we go to the denominator, we've got T on the bottom, and then we've got seconds on the bottom. Again, matching up. I see some of you guys are asking, how did I define R as 10? Full disclosure, this line should have been in the original problem. I must have forgot to type it in when I did it, so I just added in later, okay? So they've got to give you, to finish this problem, you need to know what R is. The rate of change depends on the radius. So I just added that in after the fact. I hope this example makes sense. What I'd like to do now is look at a couple more examples with you and show you how the problems get a little trickier and how you're going to handle that. But before I go to the next example, I just want to remind you of this one thing. Identifying your variables, figuring out your dependent variables is the key to figuring out the equation you need, okay? So we're going to pay really close attention to the rates, who the dependent variables are, and then how can we create an equation based on that. So if you guys would move with me to this next one. In this example, we have the radius and the height of a cone are both increasing at a rate of 2 centimeters per second. How fast is the volume increasing when the height is 9 centimeters and the radius is 6 centimeters? Okay, so if you can picture this, we've got one of those, just a cone, and the cone is changing its size. And because the cone is changing its size, there are multiple things that are changing. The cone is getting bigger, so the volume is changing, but because the volume is changing, the radius and the height are also changing along with it. So what I'd like to do is just go through and, again, just try to focus on the key word, and those are the words that mean rate. So as we're reading the problem, first place we see rate is right here. And then we want to take that and we want to change that into some kind of mathematical notation. So when we see this word rate, it's referring to what? What is changing according to this? And this is where you're going to have to go back and read the question a couple of times. But if I ask you guys, this rate of 2 centimeters per second, what thing or what things does it refer to? You look back in the question and you see that it refers back in the beginning to both the radius and the height. So this one rate actually gives us two derivatives in this problem. So what I'm going to do is I'm going to set this up by writing d over dt, not once, but twice. And now we got to ask, what is changing? Well, rate tells us to write the d over dt. What we're pointing at tells us what's changing. So in the first one, we're going to need the radius to change because we've got the rate pointing to the radius. So again, I'm going to call that one dr over dt. And in the second one, we've got the height changing. So I'm going to call that dh over dt. If I keep reading, I'm looking for more keywords, anything that means something's changing, anything that means I've got the word rate here. So as we continue to read this, do you guys see any other words that would imply that we have a rate? So I'll give you a second to read that and then type it into the chat if you think you see a word that implies rate. All right, and Cole, you've got fast. I've got Dan going with increasing. Both of those words mean rate, okay? When you say how fast, it's usually short for how fast is something changing. When you say increasing, increasing means something is getting bigger, something is changing. The word I'm going to use in this case, I like going with the word fast. I'm going to talk about the word increasing as well, but you're going to see why I go with fast and how increasing plays in just a second. So this is the next keyword, fast, and what's it referring to? Because basically I've circled it and now I've got to point to something. So what is changing when I say how fast? Well, in this case, I'm pointing at the word volume. So that's going to get me a third rate in this problem. Fast means d over dt. What's changing is the volume. So I'm going to go with dv over dt. So now I want to go back and read the problem again and see if they tell me anything specific about these three rates. Okay? dr over dt, they do tell me something specific. They tell me it's 2 centimeters per second. So I'm going to put that in right there. 2 centimeters per second for dr over dt. Likewise, they tell me that dh over dt, the height is changing at 2 centimeters per second. Now, if this problem had just said the radius and the height of the cone are changing at a rate of 2 centimeters per second, that's not as specific. Because if you tell me something is changing, the logical question you should be asking is, well, how is it changing? Is it going up or is it going down? The example I used today in my class was if you have a bank account and the amount of money is changing by $1,000, well, that could either make you very happy or very sad. Because if $1,000 is being added to your account, you're going to be a little happier. $1,000 being taken away, you're going to be a little sadder. So the word changing isn't specific enough. And that's where the word that you guys were talking about earlier comes in. This is where increasing comes in. Increasing tells us that the change is a positive change. So I know this is, unnecessary, but just to stress the increasing, I really want to put a plus there. I want to remind myself that we're going up by 2 centimeters per second. And the same is true with dh over dt as well. Now, obviously, if you left that out, no big deal. By leaving out, it's still positive. Where it becomes really, really important is if we're not using the word increasing and the word was decreasing instead. Okay, so just keep that in mind. I'm going to go read now more about the volume and the change in the volume. And when I go to read that one, I realize that's what this question's about. How fast is the volume increasing? So to me, this is where the problem really lies. It's about finding dv over dt. I can take a moment to try to compute the units because we should be able to predict the units. If we see a t on the bottom, the units are going to be measured in units of time. In this problem, units of time are measured in seconds. So I know the bottom unit is going to be seconds. And now we've got a v on the top, but we've got some clues about what the unit should be there. So volumes are measured by multiplying three lengths together. The unit of length they're given us in this problem is centimeters. So the logical unit for volume would be centimeters cubed. So I can take a moment right now and predict my units ahead of time. That will save me some trouble later on. So I've kind of gone through and gotten all the keywords rate taken out of this problem. What I want to do now is go through and just try to figure out, are there any other important pieces of information? So I like to organize my boxes like this when I do it. Remember, the box on the top is for the dependent variables. You only can get in this box if you have a rate, and we have not one, not two, but three rates. Each one of them has a dependent variable. So we're talking about R, H, and V being the dependent variables we're allowed to use in this problem. This bottom box down here, which really didn't play a role last time, this is where I want to put any other information they've told me, which I haven't used yet. And if you look at this problem, we see some more information that we haven't touched on yet. And that's the height is 9 and the radius is 6. Okay, so obviously this is going to play a role somewhere in this problem. So what I want to do is make a note of that so I have it someplace handy. So I'm just going to say down here that h equals 9 centimeters and the radius equals 6 centimeters. By doing this, I've kind of taken the entire word problem and just put it in my box. I can see all the major pieces of information in these boxes. I refer to this box down here. It's just something I do in my class. I call it the junk box. It's where I put any information which I think is going to be important, but I'm not sure how it fits into the problem yet. So that height being 9, that radius being 6, it goes in that junk box of mine. So the only other thing I want to say about the junk box, or in this case, the height and the radius, you have to be careful. This cone is expanding. It's getting bigger. So when I say the height is 9, is that true everywhere in this problem? When we say the radius is 6, is that true for the entire problem? And what you have to understand is, no, the cone is changing. So this height and this radius are only valid when it comes time to answer the question. Because they're not true all the time, because they're changing, they're just being used at one specific spot, I always make my students put an asterisk next to them to remind us, be careful with these two pieces of information. If we use them at the wrong time, the problem's not going to work, okay? The only time we're allowed to use these two pieces of information is at the moment we're getting our final answer. So I hope everything's making sense so far. If not, feel free to put any questions over on the side. But at this point in the problem, I've changed all the words to mathematics. And the key to this problem is that dv over dt. I'm looking for dv over dt. And to me, this right here, this means I need an equation with dv over dt in it. Because once I have an equation with dv over dt, I'll be able to solve it. The problem is, again, thinking back to my geometric formulas or any of the formulas I learned before calculus, there weren't any derivatives. So this is where the junk box comes into play. I now change the question from give me an equation with dv over dt in it to can you give me an equation with v in it? Because if we have an equation with v, because we know how to differentiate, we can manufacture an equation with dv over dt. So what equations do we know that deal with volume, radius, and height of a cone? Well, that would be the volume of a cone equation. So the volume of a cone, let me put it out there to you guys. Anyone know the volume of a cone? Can you give me an answer in the chat if you know the volume of a cone? And we got 1/3 pi r squared h. Yeah, that's it. The volume of a cone is, in fact, 1/3 pi r squared h. Now, when I look at this example, I know I want to differentiate it because when I take the derivative of that v, I'm going to get some form of dv over dt. When I take the derivative of that r, I'm going to get some form of dr over dt. And when I take the derivative of that h, I'm going to get some form of dh over dt. But if you look at our box, those are precisely the derivatives I'm able to handle. I know how to handle dr over dt, dh over dt, and dv over dt. So I am perfectly happy working with this equation. We're going to see an example later on this evening where it's not going to be as straightforward. But the bottom line right now is this equation works for us because we are using only the variables in the variable box. So as long as we keep to these variables, everything's going to work out perfectly. So we're going to take a moment. We're going to differentiate this equation. The derivative of v is dv over dt because we're taking that derivative with respect to time. On the other side, we now got to pick a rule because this is going to be a product or maybe a quotient or maybe a chain rule. I've got to pick out the right one. I see this as a product rule all the way because I've got factors. The way I always set my product rule is I put my first factor in this system of boxes. I put my second factor in the next box. And then I just treat this as two small problems to get my product rule done. So the derivative of h is going to be dh over dt because we're taking it with respect to time. The derivative of the r squared, we got to give that 1/3 pi a free ride because constants just get carried to the answer. And now I got to take the derivative of that r squared, and that's going to be that chain rule that we've been doing. So it's going to be 2 something to the first. We're going to copy the middle r, and then we're going to multiply by the derivative of that inside, and that's where we're going to get the dr over dt. So I hope you can kind of see from earlier when I said the derivative of v gives us a dv over dt. In these boxes, you're seeing the derivative of r giving us a dr over dt, and the derivative of h giving us a dh over dt. But as long as the derivatives we get are rates that are in our box, we're happy to use them. So putting this product rule together, it's going to be 1/3 pi times 2r dr over dt times h, and then it's going to be plus going the other way, 1/3 pi r squared dh over dt. So I hope you guys can read that. Let me give myself a little more space. All right. So as we look at this equation, we're trying to find the dv over dt. So we're very happy we have that in the equation. And now, what are the other things in the equation? Well, 1/3 pi to all constants. We're not going to have any problems with that. We need to know what r is, but this is where the junk box comes into play. It's time to answer the question. That's when we're allowed to use this value of r. So we're okay with the r. dr over dt, we know it's this rate over here. And h, that's also in the junk box. So we're going to be able to substitute in for all of those values. 1/3 pi are not going to be problems. Those are constants. We already said we know the value of r. And the other rate we're given right here is dh over dt. So we're going to be able to substitute in for every single one of these factors. So dv over dt is equal to, let's see if I can clean this up a little bit, 2 pi over 3 are all the constants. The value of r we're getting is 6. The value of dr over dt is 2. The value of h is 9. Now we're going to add pi over 3. We're going to have an r squared, but the value of r that we need is 6. And the value of dh over dt is 2. So we're able to substitute in for every single one of these values. Now it just becomes a little bit of arithmetic as we work this out. So that 3 is going to cancel with that 6. And we're going to end up with 72 pi in the first term, plus this is going to be 18. I'm sorry, this is going to be 6. So we're going to put a 2 there. So we're going to get 4. We're going to get 24 pi. And when we add that together, we're going to end up with 96 pi. And now the only thing you got to do is to remember to make sure you put the units in, okay? We predicted the units to be centimeters cubed per second. That's what they're going to be. So final answer, our dv over dt equals 96 pi centimeters cubed per second. Just want to take a moment to kind of talk about the AP exam and what you'll be expected to show on the AP exam and what you're going to need to get full credit. One of the questions I often get, do I need to know all these formulas? Will the AP exam provide formulas for me? It's kind of a crapshoot. More recently, what we've been seeing is the AP exam is providing most of the formulas, okay? But you should always be familiar with your geometric formulas. You don't want to rely on it, but to be honest, as you look at the last 10 years of exams, we are seeing most of the time the advanced placement exam is providing the formulas for you. So formulas, my advice is make sure you're familiar with them. That way when they're there, it's just even easier, but you don't want to depend on it. The other thing I want you to be keep in your mind is if you leave out the units, you will lose points. The AP exam will deduct points for not having your correct unit. So be very careful to make sure you remember to put the unit in at the end of the example. Okay, so we're going to take a look at another question. So I'm going to pull this up. What I'm going to ask you to do is just to take a minute and read it and then just try to write down the rates and basically the equivalent of the box I've been making. Can you fill out what your rates are and what your dependent variables are and what the junk box is? I'm going to give you guys just a minute or so to work on your own, and then I'm going to join you again, and we're going to go through this problem together. So let me just give you about 2 minutes to work on this on your own. I'll check back in with you. All right, I want to start looking at this problem together. So let's see how you did in just getting the setup. In this example, the area of a rectangle whose length is twice its width is increasing at a rate of 8 square centimeters per second. Find the rate at which the length is increasing when the width is 5 centimeters. So as you're reading it, the first thing you're doing is you're looking for those keywords. And the first keyword that I see is this word rate. Okay, we're looking for any word that means rate. So there's the keyword. What is it referring to? In other words, ask yourself, what's changing? And when you read this one, the area of the rectangle is changing. So this gets pointed back to area. So what you should have done with this particular rate is you should have come up with the derivative called dA over dt. So as you continue to read the problem, you see the keyword rate again, and you ask yourself, what's changing this time? And this time, find the rate at which the length is increasing. So we're going over here to length. So I would end up calling this one dL over dt. Those are the only two rates we seem to have in this problem. So when we go back and we ask, what do we know about these rates? We are told that the area of the rectangle is increasing at a rate of 8 square centimeters per second. So I'm going to write that in as 8 square centimeters per second right there. And then when I read about the rate of the length, that's what the question is about. So this is my question mark. So that gives me the big hint that I'm looking for an equation with dL over dt in it. Just remember, the only way we get an equation with dL over dt is to start with an equation with L. So in the back of my mind, I'm already starting to think, what equations do I know that have length of a rectangle in it? So keep that in mind as we continue to organize the box. The other thing I'm going to think about is, what are the appropriate units on this derivative? Well, L is a length. Lengths in this problem are measured in centimeters. T is a time. Time is measured in seconds. So now I'm going to go and set up the remaining pieces here and try to organize this work. Two rates, two dependent variables. So my variables are A and L. Keep in mind, we need the equation with L to get dL over dt. And we're certainly open to using an equation with A, because if you take derivative A, you get a dA over dt, and we know how to handle both A and L. So we're perfectly happy using those. The only other thing I need to do now is look to see if there's any other information I haven't used yet. And there is one more piece of information down there at the bottom, and that says we're looking for all this when the width is 5 centimeters. So to me, that is going to go in my junk box. And it deserves an asterisk to remind me that it's not always 5 centimeters. So we're going to have to use this only when we're trying to find that final answer. Don't use it too early. The width is changing. We got to allow it to change until the very end when we're plugging in to find the right answer. So at this point in time, what I hope you picked up on, and what I'm trying to make clear to you, is the key is finding the equation. Because once we have it, we can take the derivative. We need an equation that has L in it for sure, and we certainly don't mind using A. So I'm thinking about A and L, and I'm thinking about areas of a rectangle. The first equation that jumps into my mind is A equals length times width. So how do we feel about this equation? This equation is good because it's got the A and it's got the L. However, it has a W. And I see a clause over here coming in saying, I've left something out, and I think she's caught me on this, because she's right. We do have one more piece of information from before. We've got a length that's twice the width, and I did not use that. That's something I want to keep in mind. So I am going to put that in the junk box, that the length is twice the width. So thank you for pointing that out. But going back to my equation, I've got A and L and W. Now, 3 variables in my equation, but only 2 variables in my junk box. That's going to create a problem, okay? If I were to differentiate this equation right now, I would end up with 3 derivatives. I would end up with dA over dt, and I'm happy with that. I would end up with dL over dt. I'm extremely happy with that, because that's what I'm looking for. But then the dilemma I'm going to run into is I'm going to get a dW over dt. And I am not prepared to handle a dW over dt in this problem. I have no information about it. I might be able to find some more if I want, but I would prefer to avoid it if at all possible. So as I look at this equation, I'm happy with A, I'm happy with L, I am not happy with that W. So the question becomes, can I get rid of it? Can I do something with that W to make it go away so I'm not going to end up with that dW over dt that I'm going to get if I do the derivative now? And that is where the junk box comes into play. You guys pulled it out. You saw it. L is equal to 2W. So I now have a relationship between L and W. Well, of L and W, which is the variable I prefer to use in this problem? I prefer to use L. So I can manipulate this, and if I do it correctly, I'm going to find out that W is the same as using 1/2 L. So CJ, you've got it. So instead of using W, I'm going to take this piece of information and plug it in for W. If I do that, A now equals L times 1/2 L, which is equal to 1/2 L squared. And now when I start with that equation, I hope you understand that this is going to work perfectly because the A is going to give me a dA over dt. I know how to handle dA over dt. The other side, the L is going to give me a dL over dt, but that's the way I'm looking for. So I'm happy to get it. So I'm just going to take the derivative. The 1/2 gets a free ride. And remember, because L is not the independent variable, because time is the independent variable and L is the dependent variable, we got to use a chain rule on this. So the chain rule is going to give us 2 times something. Copy that inside of L. The derivative of L is dL over dt. Clean this up by doing some canceling. And now we know that dA over dt is equal to L dL over dt. At this point in time, I want dL over dt to stay in the problem. So I need to figure out what L is. I need to figure out what dA over dt is. But if I go back to my box, I've got everything I need. So dA over dt, just move this over. dA over dt is going to get replaced with 8. L is going to get replaced with, well, I go to my box and I'm looking for L and I don't have it, but I have the next best thing. I know that W is equal to 5 when I want to answer the question. So now this is what I mean. I can't plug this in too early, but it's now the time to answer the question. I've taken the derivative. Basically, when you asterisk something, you got to wait until after the derivative to use it. So I've taken the derivative. I know W is 5. Because W is 5, L ends up being 2 times that, which is 10. And now I've got dL over dt in my equation, but that's fine because that's what I'm solving for. So the last step here is to isolate dL over dt. And I'm going to do that by dividing both sides by 10. So I'll get 8 over 10, which is the same as 4/5. Don't leave this problem too fast because I am not done until I make sure I use my units. So L, the units of L in this problem are centimeters, and the units of time in this problem are seconds. So my final answer is dL over dt equals 4/5 centimeters per second. The important thing I want to say about this particular example is when you're finding your equation, make sure you're only using variables in your variable box. That was the key that told us we had to get rid of W. Find a way to replace W with one of your other 2 variables, and you're going to be all set. So again, keep in mind, try to make sure your equation only uses the variables in your variable box. We are going to go and jump to this example, and it's another cone problem, but I chose this problem because it's a very, very common problem on the AP exam, and students struggle with it at first. Again, I'm going to give you about a minute or 2 to read through it, and then we're going to try to set the box together and finish it. So go ahead and read this one, and I'll be back with you in just a minute. Okay, let's see how you guys have done. I've already started to kind of highlight and outline some of the more important phrases in this one, the keywords. So hopefully you're agreeing with what I've got. The 2 most important words again are the word rate. Rate, something's changing. Every time you see the word rate, it means derivative. So I've got to come up with 2 derivatives in this problem. So because I've got 2 rates, I'm going to write d over dt not once, but twice. Okay. So in the first time I see rate, I see that the rate is the thing that's changing is the height. So I'm going to call that one dh over dt. And the second time I see the word rate, I see this time the rate is pointing to volume or describing volume. So I've got dv over dt. So again, just to kind of go over this entire question, we've got a container that's an open right circular cone. The cone has some dimensions. The height of the container is 10 centimeters. The diameter is 8. Clearly, that's going to play a role a little bit. We've got water in the cone that's evaporating. So the height is changing at a constant rate. We want to find the rate at which the volume of the water the container is changing when the height is 5. So a lot of times a problem like this, it's nice to, like I said, go through and highlight what's important. It's also a good idea to come up with a picture maybe or a visual to help you understand it. First thing I'm going to do is I'm going to go back to those rates and just get that information and try and make my box. Then we're going to start looking to see if we can draw a picture to maybe get a better feel for what's going on. So in this example, dH over dt, it's changing at a constant rate of 2 centimeters per second. So we know dH over dt is 2 cm per second. 2 centimeters per hour. So I've got that. When I go to the dV over dt, that's the one we're trying to find. So I know that's the question mark. Okay. So now I want to put the units in on that so I know what I'm looking for. And because the volume is the top, we know that the units are going to be centimeters cubed. Because time is the bottom, we know the units is going to be hours. Okay, so that's what we've got. From here, I really want to focus on my dependent variables. And I've got 2 rates. So I've got 2 dependent variables. V and H are our dependent variables. And now, do we have any other pieces of information that's important? Well, we do. This is where we know the height of the container is 10 centimeters. We know the diameter of the container is 8 centimeters. Is this information changing? Okay, that's the question we want to ask. Is this information changing? Since this is of the container, it's not. Okay, this is static. This is for the container, so I don't need the asterisk. Now, I see someone's got a question over there, and I appreciate that question because we're going back and we're looking at the dH over dt, and I've put the dH over dt at 2 centimeters per second. The question is, wouldn't that be -2? Well, because dH over dt is a derivative, if the derivative is negative, that means it would be decreasing. Because this is evaporating, that's exactly right. We do need to go back and put a -2 in there. So that's a great catch. We need a -2 centimeters per hour for that. So if the if the amount is increasing, the derivative would be positive. If the amount is decreasing, the derivative needs to be negative. This height is definitely decreasing. We need negative. Okay. So now we're going through, and again, we've got a right circular cone. All right. So what we want to do is we want to think about what that would look like, a right circular cone. So to me, what I think of when I hear a right circular cone, that's a cone that is kind of made out of a right angle. So the cone actually would look something like this. Okay, this would be our right circular cone. And what we've got is we've got water in this cone. So the water has a level, something maybe this far up. And that water is evaporating. So the idea here is to label this the best we can so we get an idea of what's going on geometrically. Well, we know that this cone has the dimensions where the height is given by 10 centimeters. We know the diameter of this cone is given by 8 centimeters. Okay, so now the idea is, can we work our variables into this problem somewhere? Because to me, a good picture is a good picture if it's well labeled. All right, so the labels we're looking for are the V and the H. Well, V is the volume of the water and H is the height of the water. So the height of the water can be labeled there. That's the height of the water. The V, the volume of the water, it's kind of hard to do it, but we're just saying, hey, there's water in there and it's got a volume. So this is the picture we're dealing with. This is the shape we've got. The idea now is to come up with an equation that uses our variables. And remember, the most important variable to use is V, volume of a cone. So the equation that I am going to be looking at to start with in this problem is that volume of a cone equation. So we saw earlier today, the volume of a cone equals 1/3 pi r squared h. So my question to you guys is, when you look at this equation, what variables am I happy to see? And what variable am I not so happy to see? As you look at it, it should be clear that we want to use v and we want to use h. The variable we don't want is r. So this whole problem hinges on, can we find a way to replace the r? Is there a way to get rid of the radius of this shape? Okay, so this is a classic calculus problem. And once you learn the trick, hopefully you'll remember it because you're going to use it all along. So I've got some people saying, hey, isn't r going to be half the diameter? Absolutely, r is going to be half the diameter. But the problem is I can't trade r for diameter because I need to only use v's and h's in this problem. So I do like the idea about using the diameter because we do have information about the diameter. So the first thing I'm going to do is take that advice, and I'm going to change this to 1/3 pi, and instead of r squared, I'm going to use d over 2 squared, okay? Because r is half the diameter. I'm going to clean this up a little bit, and I'm going to end up with 1/3 pi, and now I'm going to get d squared over 4 times h, and I think I'm just going to change that to pi over 12 d squared h. So I hope everybody is following along with me on this, and we're going to get pi over 12 d squared h. So now I've got v I'm happy with, I've got h I'm happy with, I don't want the d. How do I get rid of the d? And now I see Flanny over in the chat is all over it. She knows the trick. We've got to look at this as a two-dimensional picture. We've got to use similar triangles. We have got a big triangle formed by the cone itself, and then we've got a smaller triangle formed by the water. These are similar triangles. We've got to go back to our days of geometry and use it. So we know this dimension up here is 8, and this dimension over here is 10. But we know for the smaller triangle, this dimension here is our h, and this dimension up here is our d. So we can now set up a proportion. So using the idea of similar triangles, we set up a proportion. And the way I like to do it, in this case, I'm going to do the small triangle compared to the big triangle. Okay? So when I go small triangle, I'm going to have an h on the small triangle, compare it to its corresponding big triangle. It's going to be h to 10. And the other fraction, I'm going to go small triangle, which is d. Compare it to its corresponding big triangle. The big triangle is 8. So I've got h over 10 is equal to d over 8. Keep in mind, we're trying to replace the d. So if I multiply both sides of this by 8, d is going to give me 8 over 10h, which is the same as 4/5 h. So no matter where we are in this problem, d is going to be the same as 4/5 h. If I take this and bring it over here, I'm going to take this volume equation, which is v equals pi over 12, and now I'm going to replace my d with 4/5 h. And when I do that, I'm going to get the volume equals pi over 12. I'm going to get 16 over 25 h squared times h. And now we're going to simplify this a little more. We're going to get rid of a factor of 4 in both of those. And we're going to get that v equals pi over, well, 4 pi over 75 times h cubed. Okay? This is the key to this problem. This is the hard part. And the thing is, it doesn't require any calculus. This is you being very familiar with your pre-calculus, with your previous courses, and being able to use it. Because at this point in time, what we now have is we have an equation, v is equal to 4 pi over 75 times h cubed. Well, if you remember, those are precisely the variables I want to use, v and h. Those are the variables that I have rates for, v and h. So since I have this, I can now take the derivative and I can finish this problem off. So the derivative of v is dv over dt. The 4 pi over 75 gets a free ride, and the h cubed is a chain rule. So it's 3 something squared copy h in the middle, dh over dt is the derivative of the inside. So using all of our information, we can now hopefully finish this off. What we're going to get is dv over dt. I'll write it up here. I'm going to take this 3 and that 4 and put it, actually, I'm going to take that 3 and cancel with the 75. So I'm going to end up with 4 pi over 25. I need to know my value of h, but they told me my value of h was 5 centimeters, so I should have put that in my box with an asterisk because now it's time to use it. 5 centimeters goes in here. And now dh over dt, that was given as a rate of -2 centimeters per hour. So we can get a final answer here. dv over dt. 5 squared is 25, so those are going to cancel. So we're going to end up with -8 pi centimeters cubed per hour. And that's going to be our final answer. Okay, so I know there's some questions over in the chat. Let me take a look at that and give you some feedback. On the exam, is it a good idea to reduce as far as I can, or will I lose a point if I do not reduce? So the answer to that question, if it's free response, you do not have to simplify your arithmetic statements. You don't have to do any arithmetic at all. So if you're in the free response and you get an answer of 2/10, you do not have to make that 1/5. You can leave it 2/10. If you're on the multiple choice section, the answer you get has to be one of the answers that's one of the 4 choices. They are going to simplify those answers. So you are going to have to simplify answers on the multiple choice to match your answer to their answer. Okay. But again, free response, no simplification is necessary. Multiple choice, you're going to have to simplify to match it. So I hope that answers your question. What I want to do just very briefly here is just recap a couple of things about the related rate problem. Okay. What I hope you've got from this evening is going from the English words to the mathematical symbols tells you what equation you need, okay? Every time you see the word rate, you're going to come up with a new derivative. Every time you have one of these derivatives, that's going to tell you a variable that you want to have an equation with. Start with any equation that has those variables. And this one, we start with v equals pi r squared h. I had a v, I had an h. Those were great. I didn't want an r. Your job is going to be able to reduce that equation from all the variables to only the variables you want. Once you've got the variables you want, now it's time to take the derivative. Take that derivative, plug in your values, solve for the rate you're looking for, and you're going to get the answer every single time. Okay? Related rates is a big topic on the AP exam. There's usually a lot of questions about it. I'm quite confident that we're going to be doing another stream, a follow-up stream, kind of related rates part 2. When that date comes up, we'll be sure to post it on our social media. I hope this evening you guys got a good introduction to related rates and have an idea of where to go and how to start. Any comments you have in the chat would be greatly appreciated. If you've got feedback, please let me know. If you thought tonight went well, please say so. If you thought we needed to do something a little bit better, let me know. And if you have any topics that you'd like to see us stream in the future, again, please put that over in the chat over there. Our time for this evening is just about up. There was one more question that was asked. I'm just seeing it now, and I just don't want to hit this one. Would the process change at all if the rate wasn't constant? Because what you saw in a lot of the problems tonight, we had a constant rate. The answer to that question is no. It wouldn't change at all. But if the rate's not constant, you just have to make sure you're using it at the appropriate time, okay? So I'm going to make sure that in our follow-up stream for Related Rates Part 2, we'll do a problem that has a non-constant rate so we can see that. But the bottom line is this process will remain intact even if the rate is not constant. So again, any comments, any feedback, let me know. I hope this was really useful for you guys. I appreciate you guys watching tonight. So just give me some feedback, and we'll see you next time, okay? So check your social media, and we'll let you know what our next streams are going to be. Thanks for joining us this evening, and have a great night.